Okay, nochmal neu anfangen. Welcome to this presentation about geodesic distance measures. Geodesic is a term that stems from geodesy, meaning the science of measuring the size and shape of the Earth, and originally meant to measure the shortest route between 2 points on the Earth's surface. And that is what we're going to try to do today. Let's move on to the structure. At first, we'll talk about the Haversine formula, and then about the Vincentize formula. Those two are the most commonly used formulas nowadays for calculating distances on a sphere or a spheroid. Then we'll move on to comparing the data that we retrieve from calculating different routes with those two formulas, and we'll end it with overview of the results and the lessons that we learned. So the Haversine formula, it's a great circle distance measurement, meaning that we assume the Earth is one perfect sphere. It's made up of infinite amount of great circles and has a constant radius. Right under the first bullet point, we see the Haversine formula, with d standing for the distance between point 1 and 2, r being the radius, and theta and lambda being latitude and longitude. Now, if we inverse the Haversine, because of its relation to the sinus, that being that Haversine of an angle equals the sinus of half of that angle squared, we can either use the inverse Haversine or the arcsine and then square root everything within the brackets. And so we are going to do the latter part, and then we can multiply by r so that we can solve for the distance. And then all we need to do is to insert theta and lambda, meaning latitude and longitude, and we get our distance between those 2 points. The Haversine formula has a big advantage to its predecessor, the spherical law of cosine, which is that it is very accurate for small distances. The spherical law of cosine was struggling with that because a cosine for small angles that relate to those small distances is very inaccurate, while sine and tangent are very precise for that measure. Let's move on to Vincenti's formula. At the base of his formula is the assumption that the Earth, in fact, is not a sphere, but an oblate spheroid, meaning that it is not perfectly round, but that it is thicker at the equator and smaller at the poles. And because our Earth, in fact, is an oblate spheroid, this formula is much more accurate, up to an error margin of a maximum of 0.5 millimeters. And it also has a problem, though, that being that of antipodal points. Antipodal points are points that are on almost or exactly the opposite sides of the globe. Meaning if you have one point and you draw a straight line through the center of the Earth and then keep going until you meet the surface on the other side, that is the antipodal point. And now if you have 2 points that are within 75-kilometer radius of each other's antipodal point, then this formula can become unstable because it's an iterative formula, and it will lead to iterations that will go back and forth but not converge to the distance between those 2 points. Now, these are the routes that I calculated. I made the assumption beforehand that going north to south, meaning differentiating the latitude and keeping the longitude relatively even, would have a bigger impact on the error that the Haversine formula has, rather than keeping the latitude straight and changing longitude. That was because I was suspecting that the bulge at the equator would have a bigger impact on the error margin than the different sized radius that the Vincenti's formula has for different parts of the Earth. Now, if we look at the longitude and the routes that go west to east, we see two things. First, that obviously for very small routes, very short routes, the absolute error is very small, and for longer routes it is bigger. We also see that the Vincenti's formula for every single route calculates a greater distance than the Haversine formula. Now, this is to be expected because the radius on the equator, meaning the longitude radius for the Vincenti's formula, is much bigger than the radius for Vincenti's north and south rotations. If we look at the data, the Earth radius is to be estimated between 6,353 kilometers up to 6,384 kilometers on the upper end of the scale. And so there are to be expected certain infrequencies. If we look at the latitude now, what we expected was that there is a higher error margin. And comparing the error margin of the longitude being 0.25%, almost 0.26, and the average error in the latitude differentiation being 0.36% almost, we see that there is a much higher error. And we also see that it is above the 0.3% that are commonly suspected for the Haversine formula to exist. Another observation that we see is that this time the Haversine formula almost exclusively calculates a greater distance, with the only exception for Reykjavik and Tenerife, which both are islands on the ocean, which might have an impact, but we don't have enough data to back that up. Overall, what we can summarize is that Vincenti's model, using those different radius for different parts of the Earth and accepting it as a spheroid, is much more accurate. That the Haversine formula gives us very good results on short distances, and that the greater the distances, the more inaccurate it gets. And also that differentiating latitude has a much bigger effect on the marginal calculation error than differentiating longitude. Thank you for watching this video and have a great day.